Okay, good morning, students, and welcome to today's session. So we will now move on ahead of kinematics in one dimension to a more general application of kinematics concepts. We will start with two-dimensional or general kinematics with the concept of projectile motion or motion under gravity, but when the projection happens in what we call an oblique manner, that is, it is not a vertical projection, but the projection velocity or the initial velocity with which an object is thrown has got both the components, the horizontal as well as the vertical component. Okay, so let's begin. So today's session is kinematics session 5, I believe. So in general, we have now moved on from kinematics in one dimension to kinematics in 2 or 3 dimensions. We'll start with the first thing, which is what is called projectile motion. That is motion under the action of gravity with what is called oblique projection. So the term oblique projection, this means that let's say we are projecting from the ground level. So the projection velocity should be like this. It should be oblique in direction. That is, it has both a horizontal component and a vertical component. So if this is the projection velocity, it's, let's say, at an angle of theta with respect to the horizontal direction. And the acceleration due to gravity vector here is like this. So the object takes this kind of a path. We'll prove very shortly that the path is actually parabolic in shape. And then it comes and hits the ground over here. So U is what we call the projection velocity. And theta is called the projection angle. Now the projection angle is defined in such a way that it is always taken as the angle made by the projection velocity with respect to the horizontal. That is by definition the projection angle. Okay, so what we observe in this kind of situation is that the motion of the given particle or object is in a 2D plane. So that is the plane of the initial velocity u vector and g. They are two non-collinear vectors. So they define a two-dimensional plane now. So the motion occurs in that plane. Okay. Of course, here again we assume that there is no other force apart from gravity acting on the body. So there is no action of wind resistance or air drag type of forces. It's only and only the action of the weight mg, the gravitational force acting on the particle, once it has been projected. To project it, of course, you are initially applying what is called an impulse. That is a large amount of force acting for a very short duration of time. But once it has left contact with whatever external agent is throwing the object or projecting the object, there is only a single force acting on it, which is the gravitational force. From immediately after projection, till impact, only mg or gravitational force So now in order to describe the motion in terms of equations, the first thing we need to do is reference frame. So our reference frame is selected here such that we generally take the point of projection as the origin of a 2D XY plane with x-axis being horizontal, y-axis being vertical, such that the motion is in the XY plane. That is U and G okay. So basically what I'm saying here is that if let's say this is our projection vector, okay, U vector, and this is our G vector vertically downwards. So these two are defining a 2D plane. Okay, so these two are defining a 2D plane. So that 2D plane is my XY plane, that two-dimensional plane. So if the projection velocity was like, let's say like this, G is always vertically downward. So now the 2D plane is this one. Okay. If the projection velocity was here, then the 2D plane is this one. So in that 2D plane, the horizontal one is the x-axis, the vertical one is the y-axis.
But we cannot shift it any way we want, right? Because then gravity also we'll have to take components of.
No, so that is the thing. No? Your 2D plane is always such that it's a vertical plane. So mg is acting along the y-axis. But your u, you're understanding now? U is this vector. It can turn like this now. So accordingly, that vertical plane can turn about the vertical axis. You're getting my point?
Okay.
So that's the important thing to understand, that we have to define the xy plane such that your u vector does not have any z component. Its u cos theta component is the x component and u sin theta component is the y component. It's lying in the xy plane. And G is of course lying along the negative y-axis. So we'll take the y-axis upwards. So that is our system of axes. So again, the thing is, you are free to select any axis you want to. For some other reason, if you want to select, the origin somewhere else, not at the point of projection, there's no boundation. But in the standard derivation of projectile motion and the standard formula that we'll be studying now, this is the reference frame that we select. Just a moment, guys.
Sir, I could not write the last line, sir, of the reference frame part.
Don't worry, I'll take you back there. So we have to select our reference frame such that our initial velocity vector is lying in that xy plane. It should not have a z component. That is the point in general. So this angle here is theta. And of course, the g vector, y-axis is vertical. So now when we write in component form, you can see that this particle, so at time t equal to 0, projection occurs. That means the object is thrown with the initial velocity, which in component form now we can write as u cos theta I cap plus u sin theta. Okay. And from that time t equal to 0 till this object comes back and hits the ground level. Now I'm assuming that the projection is happening from a flat horizontal plane. If the topography is different, then of course it will not hit the ground level. It might hit a higher level or a lower level. That's a different matter. But in the standard projectile motion, we'll assume that it's projected from a horizontal plane and it comes back and hits the horizontal plane. So from t equal to 0 till impact, the acceleration of the particle is minus g j cap. So you can see it's a case of uniform acceleration. It's not uniform 1D motion, but it is uniformly accelerated motion, because the acceleration vector is a constant. So it's uniform acceleration in 2D, in fact. Okay, so I'll take you back to that earlier note. So this is how I've implemented that concept of reference frame below.
So, sir, what we're trying to say is, if normally I would take pointing around the right x-axis, which is pointing to the right. But if it suddenly changes, if the u is out of the screen for me, which normally would be z-axis, then I'll shift the entire plane so that
Yes,
y-axis remains the same and x is towards me.
Yes, beta. You have to turn the x-axis in such a way then that your u's horizontal component points along the x-axis.
Okay, sir.
You understood the point? No? Like suppose I have projected the particle such that u's x component is towards the east. Okay, then my x-axis is towards the east and y-axis is towards the north. So my z-axis will become towards south. Right?
So south. So how is z towards the south? It should be out of everything, no?
No. So y-axis is vertical, no? So if you're looking at the horizontal plane from above, if this is the east, okay, this is the south. So this southeast direction, this is basically which plane? It's the horizontal plane, no? And here gravity is going into the plane. You understanding, no? Gravity is not towards north. Gravity is vertical.
No,
now
sir. The north south are opposite for me.
North south are opposite, that's all right. But the thing is, gravity is not in the horizontal plane. No? Gravity is vertical.
Yes, sir.
So y-axis is perpendicular to this plane. No? So Z axis is in that plane. No? Okay,
Yes, sir, right.
so suppose
Can you
this
please
is,
show that graph once again?
yeah, I'll show just a second. See, suppose this is your horizontal plane. So this is pointing eastwards. This is pointing southwards. So this is north, right? This is west. So in this 3D picture now, where is your y-axis? It's perpendicular to all this, no?
Yes, sir.
So your y-axis is here. So, I mean, this is the vertical. Okay. Now, suppose I throw an object from here like this, that when I drop this perpendicular, the u's horizontal component actually lies in this direction. So let's say this is u horizontal, and obviously vertical will lie along the vertical direction. Then what I should do in this case, what I should do is I should take my x-axis towards the east. Because the motion will happen in this plane. No? It'll come and hit the east axis again. So I should take, in this case, I should take this as my x-axis, this as my y-axis. Okay. But for some reason, suppose I projected in this kind of way next. This is south, this is east. Now suppose I projected the particle in such a way that the u vector's horizontal component lies in this direction. So it lies in the direction of southeast. So this angle is 45. Okay. So then what I should take? I should still take my y-axis as the vertical. Okay, but I should take this as my x-axis because it will come and hit this point somewhere here. Understanding now?
Yes, sir.
So this I should take as my x-axis. Take that as my y-axis. Okay, because this motion will be such that. So here now what is happening in this case? Two vectors horizontal component u cos theta lies in the southeast direction. So in that case, the motion will be in a vertical plane formed by the vertical that is opposite to gravity and the southeast axis or the southeast direction. So that's why we'll take this as our x-axis and we'll take this as our y-axis. Whereas here what is happening, it's in this case u cos theta lies to the east. Okay. So therefore the motion is in a vertical plane formed by east direction and gravity's direction. So here the z-axis will point towards south. Okay. Here what will happen? My z-axis will point somewhere here now. In this case, my z-axis should be in this direction. This will become my z-axis. Okay. So here okay, so I'll bring you back to those examples, but I hope it is clear what I'm saying over here. That
Yes, sir.
So,
however you point your u vector, the motion will always be in a 2D plane. Yes, Ibrahim.
so won't there be like any other acceleration which is happening along the motion?
Not if we don't consider other forces like air drag or resistance forces. So it will only be G. Once the object is projected, na, like when you throw a ball with your hand, for that millisecond or so during the throwing action, your hand is in contact with it and you're applying a force. But once the ball loses contact with your hand, you're not influencing it anymore. Na?
Okay, sir.
Got my point? Na? So from
Yes,
that
sir.
point onwards, if the ball is made of some like high density material, not made of cotton wool or something like that, then you can more or less neglect the air resistance acting on it, unless it is very windy conditions. Of course, if you give the ball a spin, then because of something called Magnus Effect, the way the pressure of air changes on either side of the ball, there is a net air drag force also that acts on it. But let's assume we are not doing all that over here. Okay. It's an ordinary case of taking an object like a stone or something like that and just throwing it in the air in non-windy conditions. Okay. So it will only, more or less, it will only be influenced by gravity. There will be a small amount of air resistance force acting on it, but that will be negligible. Like if the weight of the object is, let's say, a few newtons, that air drag force might be in, something like 10 raised power minus 4 newtons. So you can more or less neglect it. Even in a practical experiment, I'm saying. Here, of course, we'll assume it is zero air resistance force. Okay, Ibrahim, so hope the point is clear.
Yes, sir.
Okay, so the whole point is like, as long as we are able to say there's only mg acting on it, there is no other force acting on it like air drag or wind resistance, then we can be sure that the motion will happen in a two-dimensional plane. That is a plane formed by the initial velocity vector u and the acceleration due to gravity vector g. Because it's an oblique projection, so u and g are what we call non-collinear vectors. So remember, two non-collinear vectors always define a two-dimensional plane. The moment you bring a third vector into the picture, the third vector may or may not be coplanar. Now you know the condition for coplanarity also, that A dot B cross C should be 0 if they are coplanar and all that. But here there's no third vector, so we don't need to worry about that. And in fact, we already know that U and G are non-collinear, so they have to define a plane. Had they been collinear, that means U would have been a vertical projection. So it's the case of one-day motion under gravity. So whatever be the direction of U, whether your U cos theta is falling in one of the geographical axes or it is falling somewhere in between, like in my second example, but the motion will still be in a two-dimensional vertical plane. Okay, imagine a piece of paper and you place that piece of paper such that the U vector also lies in it and the vertical axis also lies in it. So that piece of paper forms that vertical plane in which the motion is happening. You can actually draw the path of the particle as it goes up and comes down, hits the ground again on that piece of paper. So it's a two-dimensional motion, projectile motion. Okay, so once you understood our reference frame concept, now we can, we already defined the two quantities, initial velocity and acceleration, in component notation. Now we can go ahead with the kinematics part, that is, given the value of u and given the value of a, how we can predict the motion of the particle, the displacement, the velocity, instantaneous displacement and velocity as functions of time. Okay, so in a standard picture, because it's two-dimensional, after all, the motion is happening in a plane, we don't draw a three-dimensional diagram. We just look at the two-dimensional plane in which the motion is happening. We just look at it side on. So next thing what we do is that we express each component of motion separately. So having written the two vectors u and g in component form, So this is the projection at t equal to 0. Now, after some time, let's say the particle has reached here at some time t. So its velocity vector has changed to some v, and its position has become some x comma y. It started from the origin. Okay. So at t equal to 0, the position vector of the particle is at the origin, okay, and the velocity vector of the particle is u cos theta I cap plus u sin theta j cap. So at some time t, the position vector of the particle has become x I cap plus y j cap. The velocity vector has become some vx and some vy. So now the thing is, we want to find these things. We want to find position and velocity, or displacement and position. So you can even see that the displacement basically x I cap plus y j cap, because we have taken the origin where it started. So the displacement in general in a 2D motion, what is the displacement? It is position at time t minus position at 0. This is the initial position. So in this case, the initial position is actually the origin. So it's the 0 vector, the null vector. So the displacement is same as the instantaneous position. So these two are instantaneous position and displacement vector. Sorry, position and velocity vector. Instantaneous position and velocity equal to t. So we want to find these out now. So what we do here is we actually look at the components of motion. Okay. So motion along each axis. So horizontal axis, so you can see the initial velocity is u cos theta at time t equal to 0. And most importantly, the acceleration is 0. Whereas the vertical axis or y component of motion, so in that, what is happening is that the initial velocity with the proper sign convention is u sin theta. Okay, but the acceleration is minus g. So what is happening is, along the vertical axis, it is a uniformly accelerated motion. I mean, you can say it's a deceleration, but the thing is the acceleration vector is constant. Whereas along the horizontal axis, it's a uniform motion. That is, there is no acceleration. So the acceleration So in general, in vector form also, when we talk about the 2D motion, we'll say it's got a uniform acceleration. That is, the acceleration vector is a constant. It does not change with time. But when we divide the motion into components, right, let me.
So what heading are we supposed to write this under?
This is all under projectile motion. So now we are looking at instantaneous position and velocity, how to derive the formula for those. Okay, how to write r vector as a function of time and how to write v vector as a function of time. So what we do next is, from this vector analysis, we divided it into two individual components. So the horizontal or the x component of motion, this is how it evolves. It's got an initial velocity of u cos theta, but no acceleration. So it will be a uniform motion along the horizontal axis. Whereas along the vertical, it's got a uniform acceleration of minus g j cap, or simply minus g. So it is what we call a uniformly accelerated motion along the y-axis. This is a uniform motion. There's no acceleration. And this is, on the other hand, a uniformly accelerated motion. So now from this information and this information, we can see that at time t, the x component of velocity will remain constant. And the x component of displacement will become that constant velocity into time. Whereas at time t, from my experience in vertical motion, now we can say that Vy will become u sine theta minus gt. And the y component of displacement would have become u sine theta t minus half gt square. Because it is uniformly accelerated motion. Whereas this one is because it is a uniform motion, that is, there's no acceleration. So imagine a ball that is going in this projectile motion. If you look at the shadow of the ball on the ground, that is how the x component of motion actually looks. So that shadow on the ground will be moving in such a way that its velocity Vx is constant and its displacement with time is therefore linear with respect to time. But suppose there's also a vertical wall at the point from which you had projected it, and you're throwing some light horizontally on that ball. So as the ball is moving in the projectile motion, it's also casting a shadow on that vertical wall. So how that shadow is going to look? The shadow is going to look how we've described the motion on the right hand side, the y component. That shadow will just look like a vertical motion. The shadow is going up and coming down as the ball is going in this kind of projectile motion. Its velocity as a function of time is like this. The velocity first decreases in magnitude as it goes up, stops for an instant at the top, and then it descends. So it's that symmetrical ascent and then descent motion that we've seen in vertical motion before. But now for the overall ball, what's happening? These two things are happening simultaneously. So as it is moving, both the x and y coordinates are changing in such a way that the x component is changing, or the x coordinate is moving uniformly with respect to time. Whereas the y coordinate, it is doing that thing. It's ascending and then descending in a symmetric manner. As it ascends, the speed of the y coordinate decreases. Then as it descends, again the speed increases.
So what if we throw the light at it at some angle?
Yeah, so then also, like, what will happen is if you throw light at an angle, but there is a wall present somewhere, a vertical wall near about the projection point, okay, then it will cast both the shadows now on the vertical plane as well as the horizontal plane.
Yes, sir. But sir, how will the shadows move?
Just like I explained over here, the shadow on the horizontal floor will move according to the equations on the left, and the shadow on the vertical wall will move according to the equations on the right. You'll see both the shadows moving simultaneously. Okay, so actually the word projection only in vectors, it comes from, like, comes from an idea of shadow now.
So that
Yeah, beta, what was the question?
I'm not really, sir, able to get, sir, why irrespective of the angle, the shadow will look the same.
Which irrespective of angle nahi beta, because see that cos theta and sin theta term are there, no?
And sir, what will be the change?
What will be the change for what beta?
I'm wondering, sir, how will the shadow move when the angle becomes theta, which is not 90 degrees or 0 degrees?
If theta was 0 over here, then you are projecting it along the ground only, no? So there is no vertical motion. So you can see your uy is 0.
No, sir, it's not angle of projection. So the angle light has with the ground.
Forget about that. No? That makes no difference, beta. Because see, if light rays are falling like this, no? Light rays are falling like this, that means there is light falling vertically also and there's light falling horizontally also. It makes no difference, no? You understanding my point now? So if this is this thing, there is light reaching the ground also, okay, and there is light reaching the wall also. So if an object is over here, it's obstructing the light that would have reached here from the vertical component. It's obstructing the light that would have reached here. So it will cast both shadows now.
Okay, sir.
But for the moment, don't complicate things so much. Now, just imagine that you're doing one thing at a time. Or just imagine, there are two mirrors. Just imagine the ground is a mirror, horizontal plane is also a mirror, and here the YZ plane is also a mirror. Okay. So when you look at this from top, you will see the, the image of this object on the ground. You know how image formation happens in light.
Yes, sir.
So it doesn't matter where you are seeing it from. Whether you are seeing it from here or here, you will see if this is an object, you will see its image here only. Because light coming from here
Yes, sir.
will be like this only. So two rays which are very close to each other, when you project them back, they will appear to be coming from here. But same will happen for this guy also. If there's another observer here, he'll receive this ray of light. Another one, just imagine very close to it. So when he projects these back, they will appear to be coming from here. Understood the concept of shadow also now, no? Shadow
Yes,
is just the opposite of this. You're blocking that light. So, so if you imagine the ground, that is your XZ plane is also a mirror, and your YZ plane is also a mirror. So as you see the image of that moving object in the YZ plane, you're looking at this component of motion, the Y component of motion. As you see the image on the mirror on the ground, the the XZ plane, that is what is happening on the left hand side. That is the horizontal component of motion.
Sir, I just wanted to confirm a thing that at t equal
Yeah.
to 0, is position vector null vector or 0, or both are the same thing?
No, but see, when we talk about vector, we cannot equate a vector with 0. It has to be equated with null vector. That is the role of null vector in vectors. You're getting my point?
Yes, sir. Yes.
Like if I do this a minus a, I cannot write this as 0. This is technically wrong. Because on the left hand side, I've got a vector operation. On the right hand side, I cannot write a scalar quantity. It has to be this. Okay. Or for example, if I write a cross a, now you know that that is nothing. Okay, but that nothing I cannot write as 0 scalar. I have to write it as this.
Okay, sir.
Understood? So that is like, that's an important type of vector. Just like you have unit vector is an important type of vector. It's a vector of magnitude 1. So like that, the null vector is an important vector. It is a vector of magnitude 0.
Yes, sir. Yes, sir. Got it.
Okay, so now combining the two things, we can say that therefore at time t, the instant, so why am I writing time as a vector? Yeah. So at time t, the instantaneous velocity v is now becoming what? It's becoming u cos theta. That is the x component. But the y component is u sine theta minus gt. And the instantaneous position vector will be u cos theta I cap, sorry, u cos theta t I cap. So this is the same information, but now we are just writing it in vector form. Instead of writing it separately as x and y, we're combining it as xi cap plus yj cap, that kind of thing. But more importantly now, if we look at the graphs, okay, so along the x-axis, we look at two things. We will look at Vx versus time. We'll also look at the x coordinate versus time to understand the horizontal component of motion. So this is the Vx versus t graph, and this is the x coordinate versus time graph. These are two very simple graphs because there is no acceleration along the x-axis, so this remains constant. And that's why this is a linear function of time. Whereas the same thing, if you look along the y-axis, I mean, these are all things that you know very well from 1D kinematics. But now we have to learn how to, in our mind, understand that a motion is happening in a 2D plane where these two are just projections. So actually, you have to imagine how you combine them in the XY plane. So this is how the individual projections are acting. This is how the image is acting on the mirror in the ground frame, I mean, along the floor, and another mirror on the wall. So now our Vy will be that kind of thing that we had discussed earlier. There will be some particular time when it becomes 0. And then there'll be some particular time when it becomes minus of u sine theta and all that. Okay, so we'll come back to that. And the y coordinate will be doing that thing. It will be ascending and then descending. So at t by 2, it will reach the maximum height. So exactly at that t by 2, our vertical component of velocity will become 0. So we'll discuss the analysis of this also in more detail. Capital T here is called the total time of flight. That is, it is the time at which the projectile, the object which is projected, that is only called the projectile. Returns to the horizontal plane of projection. So at t equal to t, basically, the y coordinate will become 0. This is something very important. That's how we'll develop the formula for capital T. You can see it's come back and hit the x-axis. that is a horizontal plane from which it was projected. That is the time when we can say effectively our projectile motion is over, because we are not concerned in this case about what happens immediately after impact, whether it bounces or it sticks to the ground at that point, somebody catches it or whatever be the case. For us, the motion is only between from when it was projected till it comes back to the x-axis.
Will the time taken to reach the half of the maximum height will be t divided by 4?
No, beta, because see what is happening now. Along the vertical axis, the motion is not happening with uniform velocity. So it's not, your height versus time is not a linear graph. No?
Oh, yes.
Got it, no? It's a curved graph. You can see y versus t is in fact it's a parabolic or it's a quadratic curve. So it will not have that linearity.
We'll have to
Yes,
make
you
a
will have to in that formula that y is u sine theta t minus half gt square. No? So usme we'll have to calculate using that quadratic function of time, that at what time it reaches h by 2.
yes.
Okay, so now one more important parameter for us is called the horizontal range. So the distance at which it lands, that is called the horizontal range. So when it lands on the x-axis again at t equal to t, the x coordinate at that point becomes the range because the y coordinate has become 0. So three important parameters straight away. One is capital T, the total time of flight. Okay. The other is h, that is a maximum height achieved from the horizontal plane, that is the, in this case, the xz plane. So you'll see the how to evolve the formula for h also. And the third thing is capital R, which is called the horizontal range or simply the range. So that is the distance at which it lands on the x-axis from the origin. That is the point of projection. So again, you can see that at time t equal to capital T, the y coordinate has become 0. But along with that, you can see that the x coordinate has become r at that time t.
Done, sir.
Okay.
Just
Another
a minute.
yeah. Another interesting fact that you will see here, which looks intuitive from the diagram, but you can also quite easily understand from the equations, that when it reaches the highest point, not only is the time the half, is half the total time, but the y component of velocity is also 0. So exactly at that moment, the velocity vector points parallel to the x-axis. Okay. And the other interesting thing is that the x coordinate will be exactly half the range. So we'll just discuss in detail what I said over here. But you can understand that kind of from the symmetry of the graphs only that I've drawn. Okay, so done with this partner. Like, I mean, as long as you understood it, also it's fine. We'll discuss the equations for this now next. Okay. So another aspect which I was saying over here is that at the highest point, that is y equal to h, okay, t is equal to capital T by 2, because the ascent and descent of the vertical motion or the vertical component are symmetrical. Another way to understand this is that h is equal to y's maxima. Okay, so at y equal to y's maxima, dy by dt must be 0 now. So that means the vertical component of velocity must be 0. This you can also see from this equation. Y is equal to u sine theta t minus half gt square, and Vy is equal to u sine theta minus gt. You can see from this that dy is equal to 0 at t equal to u sine theta by g. Okay. And at that time only, y will be equal to y's maxima, h, when Vy is equal to 0. So if you just go with a calculus understanding of this, that this is your Vy as a function of time. So to calculate maxima, you need to put its derivative. Sorry, This is y as a function of time. So to calculate the maxima of y, you need to put its derivative Vy equal to 0. So you get this time. Now you substitute this time. So y's maxima is equal to y at t equal to u sine theta by g. So you get y's maxima, or the maximum height it reaches, as u square sine square theta by 2g. You can go with the maxima minima method, or you can just go with the graph method, like I've taught you before. If you look at this y as a function of time is this sort of graph, not t into u sine theta minus gt. So it's a parabolic graph which has roots 0 and 2u sine theta by g. There's a half here, g by 2. Okay. So if you look at, you don't need to apply maxima minima theory. It's a simple quadratic function. So you can go with the graph method that I've taught you for quadratic curve. So y as a function of time be like this. One root is 0 and one root is capital T, which is 2u sine theta by g. You can see the second root of this. So in between these two roots, the y coordinate is a symmetrical parabola shape. So that is why it will reach the highest point at an instant when the slope is 0. So dy by dt or Vy is 0 at this point. And the time will be exactly midpoint of these two roots. So it will be t by 2. So the time will be u sine theta by g. So this is what is happening at the highest point. So put that value of time u sine theta by g in this equation. So you'll get the value of this maximum height. So it's that same thing that we've seen in vertical motion, but u is replaced with u sine theta. So you can also think of this like this, that maximum height is u's vertical component, uy square by 2g. In vertical projection, we had seen it's u square by 2g. Here it just becomes uy square by 2g, or u sine theta's whole square by 2g. Okay, now let's look at the formula for the range and total time of flight. So we've actually already seen it in that y versus t graph. So at t equal to capital T, what happens is that your y coordinate becomes 0 because it returns to ground, basically, which is the x-axis. Okay. So just repeating that analysis. That second root of this equation so that means the time of flight is the second root, this one. Or the way I prefer to remember this formula is that it is 2 times uy divided by g. So just like in a vertical motion, it is 2u by g. Here, the vertical component of initial velocity is uy. So the formula remains the same. It's 2 times the vertical velocity divided by g. But the vertical velocity is now u sine theta. Or the vertical component of velocity is u sine theta. The next thing, the horizontal range. That will also come from this only, because the horizontal range is nothing but the value of the x coordinate at the time capital T when it hits the ground. So x is equal to r at t equal to capital T. So x in general is u cos theta t. Therefore, r is equal to u cos theta into capital T. So we have this standard formula. Just applying the trigonometric identity, this becomes the formula for the range. Okay. But for many reasons, I don't prefer this formula. I prefer another way of writing it, which I'll show you next. Okay. But anyhow, this is the value of range in terms of u and theta. Okay, now another way to understand this formula is that it is ux into time of flight. So it is ux into 2 times uy divided by g. So this is how you interpret the formula in terms of the individual components, ux and uy. Whereas above is the standard formula, how you interpret it in terms of theta and u. Just two ways of saying the same thing, but in certain situations, you will see that expressing it in terms of components will help in understanding a question faster. Now, one final thing we'll see over here, that at t equal to capital T by 2, not only y is equal to h, which is the maximum height, okay, and velocity is u cos theta I cap, because the y component of velocity is 0, but the x coordinate will be r by 2, because this is coming from the fact that x is u cos theta into t. So after which, so this fact here we can also understand this visually by just understanding this representation. And another interesting thing we'll see is that at capital T, the speed with which it hits the ground is again the same.
Sir, why will Vy be minus u sin theta?
That's what I'm showing below here. See, just follow this calculation. Understanding now? No?
Yes, sir.
So the velocity vector will become so this velocity here and the projection velocity here, they're symmetrical. You can also understand this by work energy relation, that it comes back to the ground. So the potential energy is back to zero. The gravitational potential energy. So the kinetic energy should be the same. So V should be the same as U in magnitude. Okay, so now let's understand first of all some direct type of questions. So next, let's do a numerical example. So suppose take my initial velocity is 50 meters per second in magnitude at an angle of 37 degrees from the horizontal for a projectile. So you want to find, first of all, the standard things. Take G as 10. So find the standard things, the time of flight, the maximum height, and the range. Okay. Next, find velocity and displacement at t equal to 2 seconds and t equal to 4 seconds. And third, find time t and the velocity v when the vertical position or height equals to 30 meters from the ground level. Just try this out with it. So at an instant when the vertical height from the ground is 30 meters, you have to find the velocity vector and the time. Arnav, I think you've taken the value as 30 degrees. It's 37 degrees. So the first part, you can just go with the formula method only.
So for the second part, we can write it in component form, right? The answer.
Yes, you have to give in vector form. So you have to take the standard component form. That is, the x-axis is your horizontal, y-axis is vertical. Okay. So how much you're getting the time of flight? 6 seconds you should be getting. Maximum height. From that, you should be getting maximum height as 45 meters. And the horizontal range. To 40 meters. You should be getting this. Now, I will also tell you an alternate way of doing the calculation.
Sir, I took the ratio of the maximum height to the range. Then I got range is equal to 4 into h cot theta. Is
That
it-
also you can. From this, you can see that now you'll also understand that t equal to 6 seconds is the total time. So that means that t equal to 3 seconds, it's at the highest point. So that the two times that I've given you, 2 seconds and 4 seconds, they are symmetrical. One is 1 second before reaching the maximum height. The other is 1 second after reaching the maximum height. So there is going to be some kind of symmetry in your answer also for the second part.
Velocity will be same.
Yeah, the velocities will have same magnitude, only the y component will be reversed. And displacement will also have the same y coordinate, only the x coordinate will be different.
So for displacement, we know that trajectory equation, we can substitute the value of x, which we can get by u cos theta t, and we can get the value of y. Can we do
Yes,
that?
anything which is not a standard formula like capital R or H or T, you have to use the component equations. U cos theta t for x coordinate, u sin theta t minus half gt square for y coordinate, those type of equations.
Yes.
Okay, very good. So I'm getting the correct answers from all of you. So what I'll do is for the second partner, we can just understand that UX was 40, UY was 30, and G is 10. So in general, velocity as a function of time is 40 I cap plus 30 minus 10 T J cap, and the displacement is 40 T I cap plus 30 T minus 5 T square J cap. So now you can see that T equal to 2 seconds, your velocity vector is becoming 40 I cap plus 10 J cap, and your displacement vector is becoming 80 I cap plus, which is it, 60 minus 20
40i plus 20j, right?
plus 20J. Sorry, T equal to 2 seconds, na beta?
Oh, okay, sir.
Sorry, 40 J cap, my mistake. And then you'll see that at T equal to 4 seconds, because it's a symmetrical time, I can see that 4 seconds is actually T by 2 minus 2 seconds. Sorry, capital T minus 2 seconds. Capital T was 6 seconds. So there's that symmetry. This will be 40 I cap minus 10 J cap. And this one will have the same X coordinate. But the Y coordinate, the same Y coordinate. But the X coordinate will become 240 minus 80. So that is how much? 160. This symmetry we can also represent by understanding the graphical picture. So this is when it started. It came and hit the ground at 6 seconds with a range of 240 meters. Okay. So it reached the highest point at 3 seconds with a velocity of 40 meters per second, the maximum height of 45 meters. Okay. Now these two other times are symmetrical. So you see this velocity and this velocity are symmetrical because this time T1 suppose was 2 seconds. So T2 was 4 seconds. So that is why they had a common height of 40 meters. Okay. And this one is 80 meters. So because the velocities are symmetrical and the x coordinates are also symmetrical. So again, there is that kind of symmetry of ascent and descent during a projectile motion also. Okay, now let's look at the third part of the question. So we had to find out the time at which the vertical coordinate has become 30 meters. Okay, that is, you can see in this case it's 2/3 of the maximum height. So we can use a number of methods of solving that part also. So we want to find time and velocity when the y coordinate is 30 meters. So first method is the obvious one, that your y coordinate as a function of time was u sine theta t minus half gt square. So substitute y as 30 meters in this. So you get t square minus 60 plus 6 is equal to 0. So you can see t1 is 3 minus root 3. And t2 these will be the two times. So this is your projectile path. Okay, so that kind of situation. So again, notice that there's that symmetry that t1 plus t2 is capital T. So magnitude of velocity at t1 is equal to magnitude of velocity at t2.
Sir, noted.
Done now. Okay, so this symmetry aspect is clear, I hope. Okay, so now the final thing we'll understand about projectile motion is what is called the trajectory. Okay, that is the actual path. So what the shape of that curve is, that curve along which the particle moves, is called the trajectory. So the word trajectory basically means the path. Of a projectile. So we will understand it by deriving what is called the equation of trajectory. So we have seen that x as a function of time is u cos theta into t. Y as a function of time is u sin theta t minus half gt square. Okay. So now these two equations, okay, we can solve to find a relation between x and y. So that relation, it represents a curve, okay, on which every point, that is x comma y, satisfies equations 1 and 2, where this is, let's say, equation 1, let's say equation 2. So that is, so every point is on the trajectory, that is on the path. So therefore that curve now, or that relation, will represent what we call the equation of trajectory. Okay, so just note this down and try to work this out yourself. I will discuss in just give me a moment. Okay, so how we'll do it is basically you have to eliminate time, okay, between equation 1 and 2. So what you do is, to solve this, basically we have to eliminate t, so that we get a relation between x and y. Yes, very good, Arnav, that's correct. So that equation that we get by eliminating time, that is called the equation of trajectory. So from equation 1, you can write t as x divided by u cos theta. So substitute this in equation 2. We get this relation that y is equal to so this is basically the equation of trajectory. This curve represents the actual path along which, if you trace this curve, it actually represents the path along which the particle is moving. Every point on that curve represents the position at some instant or the other. So you can notice that this is this sort of a relation. the parabolic path. Quadratic equation. Where alpha is tan theta and beta is g upon 2u square cos square theta. You can see that alpha and beta are constants. So you can also see that if you factorize this equation, you can write it like this. So often for problem solving, this second formula or the second form of writing the equation of trajectory is more useful. This becomes an important relation. So these are some additional factual matters that become very evident from equation of trajectory. And we'll see that it helps us directly solve certain type of questions. Most questions of projectile motion, other than of course standard formula based problems, formula based problems, you directly use the formula for range, maximum height and time of flight. But other than that, most problems of projectile motion will either be something where you have to involve time. So you have to use the time based equations, x and y as a function of time, vx and vy as functions of time. Or sometimes they are just geometry based, where you don't have to involve time. So if there's anything where you don't have to involve time, it's a geometry based question, then it will be much faster solving that type of a question using the equation of trajectory, which I've shown below. And specifically the equation of trajectory written in this form in terms of tan theta and r. instead of in terms of, all those complicated things, u square, cos square, theta and all. So particularly for JEE Advanced type of questions, we'll see that this last equation that we've written here, the equation of trajectory using tan theta and capital R as parameters. You see, it's a very useful form of analyzing the projectile motion. So anyhow, people, we will conclude here today, and I will send you a specific set of questions to do with projectile motion also. Okay. And next lecture, we'll keep aside some time for discussion of questions, both from the earlier worksheets I have sent as well as from the projectile one I'll be sending. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you,
Thank
sir.
you.
Bye, sir.
Thank you,
Thank you, sir.
sir. But I wanted to ask you a thing, that what's the
Yeah.
application of trajectory, equation of trajectory? Like,
Yeah, that's what I was explaining. Equation of trajectory we'll apply in the type of questions where we are having to solve something geometrically about the path, and we don't need to involve time. Those type of questions we will solve using equation of trajectory.
that's okay, sir.
Yeah, Janvi, you have a
So there
question?
was a yes, sir. So there was a question, sir, in the DPT, ma'am, of sir of calculus, which I had a doubt in, and sir, you asked me to send it to you on WhatsApp, but I think it went down in the chat.
Oh, okay. So can you just re-ping me with that question? Okay, I'll
Sir.
take a look at it today.